Reminder of what MIMS thermocouple cable is. It's where the thermocouple conductors themselves are insulated and separated from each other and the outer metal sheathing by a mineral insulant such as magnesium oxide. And the slide you're currently looking at shows the finished product, which you're probably more familiar with looking at. So into the presentation itself, and the first question, do thermocouples drift? Well, a very simple answer to that question is yes. All thermocouples suffer from the effect of a changing EMF output with time at temperature, usually a reduction in the output, particularly in the high temperature region, and this effect is known as drift. Probably a better question to ask would be, what is drift level dependent on? There are a number of factors: the thermocouple type, the environmental conditions, the temperature range of operation, and the temperatures the actual thermocouples see, just to mention a few. There are many reasons and many types of thermocouples and thermocouple designs. Some will show higher or differing levels of drift than others. But basically, most of the drift is dependent on both the thermocouple design and the environmental conditions the thermocouples actually see. As we mentioned, there are many reasons why thermocouples drift. We've mentioned a few above. But really the detail of that is for a different presentation. The point that needs to be absorbed here is there is an issue when it comes to using thermocouples for long-term high temperature measurements. So what are the current options regarding low drift thermocouples? Well, currently the range of thermocouples known as the noble metal range, or the platinum rhodium based thermocouples, the types R, S and B, would always be the choice for high temperature industrial applications. This is because these thermocouples show the lowest drift characteristics of all the common standard thermocouple types we use, mainly because of the materials they're manufactured from. However, for the same reason, both for cost and mechanical limitations, these thermocouples are not always an option for industry. The cost is a fairly obvious one: the materials they're made from, the platinum rhodium group, which can be very expensive, and also the mechanical limitations. The protection mechanisms needed for these thermocouples are usually ceramic-based sheaths, which are obviously very inflexible and also quite limited in diameters. The most practical option regarding temperature sensors is the MIMS base metal thermocouple design. This MIMS design gives practical protection for the thermocouple wires for the environments they're used in. In effect, the powder and the outer metal sheathing protect the thermoconductors themselves from the environmental attack and contamination. So for both practical and economic reasons, the Type K and Type N MIMS thermocouples are and will remain the industrial temperature of choice in this high temperature region. However, both the Type K and Type N thermocouple, particularly when we're talking about temperatures above 1000 degrees C or 1800 Fahrenheit, can also see very high levels of drift. So, why do we need a lower drift base metal thermocouple? The most widely used thermocouple types in industry, we've already mentioned, are the Type K and Type N thermocouple. The best overall option from a practical viewpoint is the MIMS design. But there is a growing demand from industry for better measurements in this higher temperature region, a more reliable measurement capability. These thermocouple designs, the Type K and Type N, have not been improved. We're using the same designs, have not been improved since the development of the Type N thermocouple itself some 50 years ago. Hence, there is a need with this demand from industry for a base metal thermocouple with a better performance, particularly in the higher temperature range.